Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering is dynamic programming. And this is the 11th topic in the list of topics which are covered in this course. And the subtopic is A, so this lecture is 11A. So basically, it looks at the basics of the application of dynamic programming in deep reinforcement learning. And this video is developed using the supplemental website ezmcq.com/GoGet, which is a personalized learning management system. So, what is the future of content delivery? That is not the future alone, that is also the present, because there are literally hundreds and millions of end users who are getting educated using the content delivery platform and mechanism, which are in hundreds and millions. So, that is the approach which is being used in delivering and explaining the concepts in this course. So, the personalized learning management system is accessible using the URL which is given in green color, and the content delivery mechanism is explained using 6 videos, and those videos are accessible using the link given in blue color. So what are those features which I've mentioned? These features consist of advanced and basic content search, which is not there in leading learning management systems. And then of course the ability to support people with visual disability, such as changing the font size, color, line spacing, and so on. And then this content is organized in such a way that it can efficiently use the limited speed, the limited space and the speed of a handheld device. And of course, you can track your progress, what you have seen, done, and what you need to do. And then, of course, you also can test yourself online in real time, your knowledge assimilation and knowledge capturing. So, how the content is delivered? The content delivery can be question and answer based, and it can be traditional slides based. Now, the question and answer based approach is engaging, is proactive, it promotes thinking, and of course, it is very productive also. And the traditional approach contains a lot of details. So, the approach we have been following in this course is a blended approach, which is the best of both. So, this is the list of topics which are covered in this course, and we are at topic number 11, which is dynamic programming. And this is further divided into certain number of concepts in the form of questions and answers. So this lecture 11A consists of the concepts in yellow background color, and the next set of question and answers are in green color, that is 11B. Now we move on to the details of the lecture. So we are at topic number 11A, dynamic programming. So what really is dynamic programming? Now, the word dynamic is not used in its literal meaning, and there is no such programming technique here. This is a concept, and this concept is plays a foundational role in deep reinforcement learning. How? By structuring learning and by decision making processes around recursive problem solving. So, if you recall that in recursive neural nets, uh, we looked at the hierarchy in an image also. Not looked at it, we covered the example also. So we see that this enables hierarchical modeling, right? This basically dynamic programming enables hierarchical modeling, and we have scenarios in which we have hierarchy within an image also. So what happens is that large tasks using dynamic programming, large tasks are broken into smaller ones. And what it does that it allows the agents to plan over long horizons or long periods of time. Now, by definition, dynamic programming works on dividing the problem and then combining the results. So this compositional nature lets the agents reuse parts of the learned knowledge. Okay, part of this is very interesting. Parts of the learned knowledge. Now, what it does is that it improves the learning efficiency and it increases the scalability. Why? Because you are using part of the prior thing. So, moreover, and of course, this is transparent and it offers enhanced interpretability also. Unlike deep learning, deep neural networks, where it's hard to interpret the meaning of or the aspects of different layers, it enhances the interpretability. So, what is the consequence? That it aids in debugging, and it adds and increases the trust in the system and the solution. Now, these are the strengths of dynamic programming, which are essential in deep reinforcement learning optimization pipeline. So, we are looking at these bullets here, and this dynamic programming basically algorithmic structure, bridges the algorithmic structure with the neural approximation and real world application. So, at one side we have the real world, then at the other end we have the neural approximation, and then in between we have dynamic program. So this is hierarchical structure modeling. This is inherent to dynamic programming, and which is exploited and in this domain of deep reinforcement learning. And we have seen hierarchy in recursive neural nets also. And using dynamic programming, there is better compositionality. What is meant by this? We will discuss this. Combine solutions to subproblems into complete policies. This is like a divide and conquer approach. And then is the improved interpretability. So this is a very useful thing which adds trust to the system also. I will briefly cover this example, this what is meant by this image. So in dynamic programming, especially when solving grid-based problems, so this is a grid-based problem, or problems involving matrices like shortest path, added distance, longest common subsequences, we put arrows in a matrix. You can see the arrows here. And this is a visual tool to represent the direction of optimal subproblem choices. So here's what it typically does. So this grid could be, say, for now, this basically here is protein alignment. I'll This is not part of this course, this is more of bioinformatics. So, but in a grid environment, so for example, we can have the area in which a robot is or a vehicle is moving, which is divided into grid. So there's a natural alignment. Okay. So very briefly, what these arrows mean. So with this up arrow, okay, this up arrow, what it's saying is that the value came from the above cell, skipping an element in one sequence. This is the up arrow, and then we also have the left arrows here. Value came from the cell to the left. Value came from the cell to the left, okay. And then we have diagonal arrows, quite a few here. Value came from the diagonal cell. Okay, usually it means a match, substitution, or a combined choice. That's what it means. So very briefly, these arrows indicate how the current cell's value was computed. This could be a location where a robot is moving from one cell to another. That is which subproblem it depends upon. All right. And then this basically the path taken to reach the optimal solution. We will cover this further also. And the trace back direction for reconstructing the solution if you would have to get back the entire solution. So say for example, if we have a string ABC and we have another string b is equal to a. So we have string a is equal to abc and another string b is equal to ac. What is a string? This is a string a c d e f. These are the strings. Okay. So there's something called as the longest common subsequence in bioinformatics. So if a if ai, okay, for one string, if ai is equal to b of j, then move diagonal, take the match, move diagonal and take the match. Okay. So then of course is else move from the max of left or up. So what the arrows tell is that which previous value was optimal and help construct the actual longest common subsequence. So here there is we moved down because prior there was a match E and E, there is a match. Okay, prior there is a match D and D is a match, and so on. So I cannot go more on this because this is not part of this course. Okay. So but basically this is the concept. Just moving has semantics connotations with a robot moving in a grid. Okay, so let's go into some details here. So hierarchical structure modeling. So what dynamic? So we are looking at this. So what dynamic programming does, it allows recursive breakdown of large tasks into smaller subtasks. That is independent of deep learning. Now dividing complex tasks into smaller fits naturally into hierarchical reinforcement learning or recursive neural net. Now where in that domain policies operate at multiple abstraction levels, right? So what it does, it enables the agents to learn and reason across these layers or levels. And dynamic programming supports long-term planning because as you have seen here, it supports long-term planning and structured decision making. You can see that there here also. So dynamic programming forms the base for methods like value iteration and options frameworks. So so it has many applications, and this is the natural application domain. Then better compositionality. Dynamic programming promotes modular solutions where individual subproblem results are combined, as I've shown you. Okay. So this supports policy reuse. Since we are subproblem results are combined, so that applies to policy reuse, task transfer, and simple efficient learning. This is supported. This is what is meant by better compositionality. And how it comes from? It comes from the using individual subproblem results, which is the inherent, which is the way dynamic programming works. Now, what compositionality means, the system do not need to learn the whole policy from the scratch. The whole, what is the policy? That is what was covered in reinforcement learning. So as a result, training is faster and more scalable. All right. So you see that the inherent advantages of dynamic programming are exploited in reinforcement learning and improve interpretability because dynamic programming methods update value functions in a structured and recursive way. So that way it becomes easier to understand why certain actions are chosen as opposed to what's happening in deep learning. So when we understand this, so we move from the domain of black box to a white box. So this transparency supports debugging, evaluation, and it enhances and increases trust in agent decisions, especially for real world deployments. So that's a big advantage. Okay, so if you are interested, and you should be interested, these are the details. This is a little bit of background. Then the bullets are explained in more detail, and this is the reference. Now we move on to the next concept and Q&A, which is about dynamic programming. So in the previous one, we looked at dynamic programming in the context of uh, reinforcement learning. All right. Now there's a very popular concept or fundamental concept in dynamic programming is what is the difference between top-down approach, which is called as memoization also, and bottom-up approach, which is also called as tabulation in dynamic programming. Okay. So basically, this is how we kind of traverse that tree. Okay. So this is how the tree looks like. Let's not look at this red arrows. So this is the bottom-up tree. Okay. This is bottom-up, and this is top-down. So what is happening is the order of computation changes. The order of computation changes, and of course the memory usage also changes because top-down stores values only for accessed subproblems. So that of course reduces memory load. We will discuss this very briefly. And then these are the implementation styles. The top-down uses recursion with memoization. So the code is concise, and bottom-up is more of the iterative approach. All right. So in terms of the background, the top-down memoization and bottom-up tabulation are two dynamic programming strategies that approach the problem solving or that approach the problem differently, and that is applicable for deep reinforcement learning also. So top-down is recursive, so it solves only the needed subproblem and caches the results. This is just like standard recursion. So it it is ideal for sparse or structured environments. because there's going to be less memory usage. The bottom up approach, on the other hand, computes all subproblems iteratively. So there is no putting things on the stack. So it favors speed and full coverage when there are a lot of states, so dense state spaces. So top down typically uses less memory and is easier to implement conceptually. Okay, because of its recursive nature. While the bottom up is more efficient, where every state action pair matters. State action pair with reference to reinforcement learning. So which is better? The choice depends upon the problem structure, the scale of the problem, and the computational constraints of dynamic reinforcement learning. So the computation order. Now top down solves the subproblems only when needed. Only when needed. So that is efficient for sparse environments. Why spend all the resources on trying to solve every problem? Now the bottom up approach pre-computes all possible subproblems in a specific sequence. When there are quite a few states, then pre-compute all subproblems. Why? To ensure consistency, but it can potentially results in wasted effort. Now as a result, top down is better for selective decision processes, while on the other hand, bottom up is better for almost exhaustive policy evaluation in deep reinforcement learning. So we are basically looking at this aspect. Now we move on to the next aspect, which is memory usage. Now in top down, values are stored only for the subproblem that was accessed. So as a result, the memory usage is reduced, especially for large sparse spaces. Now, on the other hand, bottom up requires full memory allocation upfront, which can be inefficient for large spaces or even moderate spaces which are sparse. So there's a trade-off, and this trade-off influences which method is suitable for different deep reinforcement learning architectures. And then is the implementation style. Now, top-down uses recursion with memoization, which is bookkeeping, which is standard recursion. So as a result, the code is concise and it's intuitive and it's conceptually simpler, but all the issues of recursion are there. On the other hand, bottom-up employs iterative loops. So the code is not very elegant. Okay, there are no recursive calls. So it is like it makes it more performance oriented, but it could be the code could be less intuitive because that's not recursive. So the choice affects both performance and maintainability of deep reinforcement learning systems, especially for real-time systems. Okay, so here are the details, further details. This is a kind of background. So these are further details and further details about those bullets also. And here are the references if you are interested in further reading. So we move on to the next Q&A. So explain using example what are hidden Markov models. Now we have not actually we in the next uh, video we'll spend more some time on the applications of dynamic programming in deep reinforcement learning. But in this video, particular 11A, we are focusing on the background and the related concepts. So one of the very important concepts is the hidden Markov models. I will explain what is. We have covered this slightly earlier also in other topics, but I'll explain this more in the context of deep reinforcement learning. What is meant by hidden? So what we have the hidden states. Hidden states is like we don't know what is causing a certain outcome, but we have the observable symptoms. So observable symptoms could be, for example, what we are seeing, but we really don't know what causes it. Okay, and then is the transition probability. So I will explain this diagram to you also. So hidden states are the true states which are not known, and observable symptoms are the partial clues from the emitted observations and the transition probabilities moving between the hidden states. So, what are actually hidden Markov models? These are essentially the tools for modeling environment with partial observability. You don't know everything, which is a common scenario in real world deep reinforcement learning. I will explain how. So they consist so what do the hidden Markov models? They consist of the hidden states, okay, representing the true but unobservable conditions of the system. We only have the observable systems that offer information. There is a lot of noise, okay, about these states, and we have certain transition probabilities that basically control how hidden states evolve over time. So together these components allow agents to reason probabilistically about the world around them and update their beliefs and make informed decisions where under uncertainty. So hidden Markov models not only provide the basis, okay, for a modeling, but also influence deep reinforcement learning methods that involves memory, that involves sequence modeling, and something called as belief tracking. So in this diagram, the hidden states, for example, are the healthy and the fever. So these are the true conditions of the person, but we don't really observe them directly. We only observe the symptoms: dizzy, cold, and normal. So these are the symptoms we can observe, but they depend probabilistically on the underlying but hidden state, healthy or fever. So what is hidden? The person's health condition, example healthy or fever, is the hidden part of the hidden Markov model. So we can directly see whether a person has a fever or is healthy. We only see the symptoms like dizziness or cold, and then we try to infer the most likely underlying conditions over the period of time. So this is how it works. So what is the purpose of hidden Markov model? The purpose of hidden Markov models, okay, is to infer the hidden states. So a sequence of health conditions, and they are based upon sequence of observations such as symptoms. Number one. Number two, to the model transitions between the hidden states. Example from healthy to fever. From healthy to fever, 0.3, 30% probability. Fever to healthy, 40% probability. Remaining healthy, 70%. Remaining in fever is 60%. And then to learn the emission probabilities, such as how likely how likely is dizzy given the person has a fever. All right. So we move on to the hidden states. So these hidden states represent the unobservable but influential part of the environment's condition, which was healthy and fever. So in deep reinforcement learning, these occur frequently in real world tasks where like agents can directly access full state information. So hidden Markov models model this by allowing the agents to reason over the distributions of possible hidden states, and that comes from the past observations. So that is essential in the task like navigation, or say for example dialogue, or say for example algorithmic trading or finance. Okay, then are the observable systems. So symptoms. So these symptoms are the emissions or signals that the agent receives at each time step. So they offer not direct but indirect probabilistic evidence about the current hidden state. So in deep reinforcement learning, these observations are used to update the states and guide decision making in partially observable environments. So this we are just touching upon this concept because there is a whole course on reinforcement learning in which these topics subtopics are discussed in significant detail with the mathematical background. And then are the transition probabilities. So these probabilities describe the likelihood of moving from one hidden state to another, which we I just mentioned. So these are crucial for prediction and belief tracking. In deep reinforcement learning, they form the backbone of model-based approaches, and they also help the agents reason about the future uncertainty and the dynamics of the environment. Okay.